Hi, good evening. I want to take a few moments and make sure that if you're feeling confused over the difference between a reflection and a rotation, you have another opportunity for an explanation. In these two problems, by the way, this is the Aaron's design problem, the top one, in order to finish Aaron's design, we had to do a reflection. For the bottom one, in order to finish Aaron's design, we had to do a rotation. All right, so let me go ahead and demonstrate and show you how the rules are different and the resulting images are different. So starting with number one, Aaron's design is created by reflecting the gray shape over the vertical line. The vertical line being the y-axis. And as you recall, in a y-axis reflection, my x comma y become opposite of x comma y. That is, I'm changing and taking the opposite of my x coordinate only. The y stays the same. So I'm going to use that rule to transform every single one of these points. Okay, so I'll start here. This first point is back by 2 up to 0. So back by 2 up to 0. And using this rule, its new ordered pair is positive 2 comma 0. So that's over to 2 up to 0. My next point, let's do this one, that's negative 2 comma 1. Negative 2 comma 1. That's going to become positive 2 comma 1. So positive 2 comma 1. This next point is negative 3 comma positive 1. And that, following this rule, I love to follow the rules, is positive 3 comma 1. So over to 3, up to 1. Okay? You can kind of see how I'm building. All right, this one up here is negative 3 positive 2. And that becomes positive 3 positive 2. And something that I want to make sure of is if I'm plotting points or if I'm reflecting over the y-axis here, which I'm doing, I want to make sure that all of my points fit the criteria for quadrant 1, meaning all the x's are positives and all the y's are positive. And sure enough, that's what I'm getting. Okay? All right, so we did this one. Let's do that one. That's negative 2, positive 2. And that's going to just be positive 2 comma positive 2. So over to 2, up to 2. All right, so we've got this one, this one, this one, this one, this one, and last is that one. Now, if you notice that last point, it is also on an axis just like this point was, the negative 2, 0. However, this point is also on my line of reflection, meaning this is the y-axis again, that's my x-axis. And if you're a point on the y-axis and if the reflection is supposed to be over the y-axis, then that means that point doesn't change. And you can see it if I try to follow the rule of going over to 0 up to 3, and I apply the opposite of x comma y, I'm still at 0 comma 3. Okay, so this point stays the same. Now my job is to then connect these points to build my mirror image of this kind of crazy looking figure. Okay? And what you should notice, I'll give it a little shade, what you should notice, and I'll take off these so you can see it a little better, okay, is for this picture, it's exactly a mirror image over the vertical line. It's just been flipped over, okay? The square was on furthest away from the y-axis. It's still furthest away from the y-axis. My longest side of this triangle is closest to the y-axis. It's still closest to the y-axis. It's just flipped over, okay? Now, if we were to continue with the directions, like you guys did in your block, then you would take each of these shapes and flip them over the horizontal line. Of course, we would want to follow the directions for, whoa, that's wrong. We would want to follow the directions for a horizontal or x-axis reflection, and we would be taking the opposite of y this time. All right, now how is this supposed to be different from the second problem? Well, let's talk about that. So it says in this problem, to finish Aaron's second design, I have to rotate the shape a quarter turn. So while my mind can picture this turning in the clockwise direction and ending up in quadrant 1, okay, I'm drawn naturally to things that are symmetrical, both in nature and in math. And most humans are. So my eyes are drawn and want to just put something over here that's exactly symmetrical to what was over there. In other words, I am leaning towards wanting to reflect this because that's how my eyes are drawn. My eyes want to create a perfectly symmetrical image. However, with a rotation, that's not going to be the case, okay? It's going to end up in a different place. So let me use a different color to show you on this one. So if I'm going to rotate the second shape a quarter turn, that's 90 degrees, in the clockwise direction, I'm going to follow the rules for the 90 degrees clockwise rotation. And as we learned today, you can see it up on the board over here, that means all of my x comma y's become y comma opposite of x. Okay, that's where I'm exchanging the x and y coordinate and taking the opposite of the x. So let's take that rule, keep that rule in mind, and plot my new points to figure out where my new figure is precisely. You can probably already predict that this 0, 0 stays at 0, 0. So let's go on to this one. This is -3, +2. So -3, +2. All right, I'm going to put the y where the x was, and I'm going to take the opposite of the x, and I get 2, 3. So that's going to be over to 2, up to 3. Oh, yep. Now this one, back by 3, up to 3. So -3, 3. And again, I'm going to take what was in the y, put it in the x, and take the opposite of the x and put it in the y. So I get the point 3, 3. So over to 3 and up to 3. All right, let's do this last one. So this is back by 1, up to 3. So -1, 3. Okay, can you see that? Yeah. And again, I'm going to put the y where the x was and take the opposite of x. So this is over to 3 and up to 1. Now, it's worth mentioning here that when we're rotating from quadrant 2 clockwise by just a quarter turn, or 90 degrees, I do expect that my final figure should end up in quadrant 1. And notice all 3 of my resulting points are positive, positive, which is good because all points are of the form positive x, positive y when they are in the first quadrant. Now, unless you feel overly confident with doing a rotation just by spotting it on the graph, I would recommend writing out all your ordered pairs. I will also show you how you could do it with a protractor, although I think that takes a little bit longer. Okay, so I'm going to connect all my points, okay? So this one goes here. These are connected, just like they were before. These two are connected, okay? This one goes right to the origin. Whoa, that's a straight line. And this one is also going to go to the origin. Okay, so you kind of get, again, that like rectangle. So right here is their rectangle. And then you get this little slice of a triangle. There's my little slice of a triangle. And then here's my big part. There's the big triangle. So I'm going to shade that in. Okay. Now what you can see here is if I were to emphasize, for example, let's see, this point, this was the negative 3, comma 2, and compare that to my 2, comma 3, so over to 2, up to 3. If I were to draw a line connecting each of them to the center of rotation, that's the origin, okay, what you would see here is a perfect 90-degree angle. In other words, when this point was transformed to that point, it moved exactly by 90 degrees. I don't know if you can see that color. Nope. It was moved exactly by 90 degrees. Okay? Yeah, you can see that. This is how one might use a protractor. If you start with your original and put the middle of the protractor at the center of rotation and then marked up based on whether it's clockwise or counterclockwise where 90 degrees is, and it would be exactly here. Now, again, that can be a little bit more time consuming, but it is another strategy, certainly, okay? I do want to point out, let me erase this green stuff, okay? If instead of rotating it, okay, if I had just reflected it, okay, if I had reflected my original figure, it wouldn't end up here. This is the result of a rotation, 90 degrees. Let me show you what it would look like if it was a reflection like we did in the first problem over the y-axis, because that's what our eyes are naturally drawn to. So that means all my ordered pairs would go from x comma y to the opposite of x comma y. So when I had negative 3 comma 2, I would now have positive 3 comma 2. So over to 3 and up to 2. They're going to overlap. That's okay. And then I had negative 3 comma 3, and that becomes 3 comma 3. So over to 3, up to 3. And I had negative 1 comma 3, and that's going to be 1 comma 3. So over to 1, up to 3. Okay, now comes time to shading it in. Okay. Okay. Can you see, I hope you can see, how the blue is a little bit over the red? The blue figure has been reflected, whereas in the red figure was the result of a rotation. If I were to take, for example, this point that I did before in green, the negative 3, positive 2, negative 3 positive, and compare it to its new point, positive 3 comma 2, and if I were to try to draw, connecting it to the angle of rotation, which is the center of rotation, which is 0, 0, this is not a 90-degree angle. It looks like it's pretty close to a 90-degree angle, but it's not, okay? You can see with all of your other points as well. So this one, which is negative 1, positive 3, becomes positive 1, negative 3. I think this is probably even more noticeable. So if you connect your center of rotation through your figure and your image, here's the angle right here, okay? That's an acute angle. That's less than 90 degrees. So overall, I wanted to make sure, and we'll go over this in class tomorrow, but I wanted to make sure that you could see the difference between a reflection versus a rotation. Reflections are pretty easy to picture and draw, just like I did up there with the first one. Oh, there we go. Rotations are not so easy. I think it's a good habit to plan out your ordered pairs based on the rule so that when they are challenging, it's just a habit that you're into, okay? Don't hesitate to send me any an email, or if your parents have the Remind app, send me a message and I'll be happy to help you out. Okay, I'll see you tomorrow and have a great night.